Okay, so we're going to start today's lesson on projectiles by simply just drawing a free body diagram for a dropped ball. So right now, hit pause, sketch a free body diagram for a dropped ball. Okay, so your free body diagram should look something like this, right? Where you got your ball, forces down, you got gravity acting on it. Now, what is the acceleration of this ball? Since gravity is the only force, our acceleration is down, and that acceleration we know is equal to the acceleration of gravity, which is 9.8 meters per second per second. All right, so if we drop a ball, we know the acceleration is down. Okay, we're going to draw the free body diagram for a ball that's been tossed in the air while it is still moving up. So this is just me tossing a ball up in the air, and as the ball goes past my head, what would the free body diagram of that look like? Well, if this is my ball, I would have the force of gravity down on it, and again, I would have that acceleration pointing down because that's the only force. Again, the acceleration is equal to the acceleration of gravity is equal to 9.8 meters per second per second. Now, the motion of the ball does not depend on the net force. So another way of saying that is the acceleration of the ball does not depend on the motion of the ball. The ball can be moving up, but still be accelerating down. This is something we covered way back in our second unit. Okay, so it can be moving one way and accelerating a different way. And it's going to accelerate in the direction of the net force or the big force. In this case, just gravity. Okay, so now what I'm going to have you do is I'm going to have you draw a third one here in just a moment. All right, so here is the third type of free body diagram I want you to do. What I want you to do now is I want you to draw the free body diagram for a ball that has been thrown sideways. So a ball that's been thrown straight horizontally, it has left whoever's hand, so it's just flying through the air horizontally. All right, go ahead and hit pause and draw the free body diagram now. All right, so what you should see here is our reoccurring theme. All right, there's our object, there's our ball. What forces are acting on the ball? Gravity. And that's it. That means that it's going to accelerate down. That acceleration is going to be equal to the acceleration of gravity, which is going to be 9.8 meters per second per second. Now, even though the velocity of the ball is this way, it's accelerating down because that's the only force acting on it, only gravity. Remember, we're assuming everything that we do here is dropped in a vacuum. Everything happens in a vacuum, so there's no air resistance, nothing else that we need to consider. Now, if the only force is down, why does the ball continue to move sideways? It's that I word. It's inertia, okay? The ball continues to move to the right even though there's no force acting on it that way, but it'll move in which way? So right now, hit pause for a second. I want you to think about this. Describe the sideways velocity of the ball, or the sideways motion of the ball. So how is the ball moving horizontally? Go ahead and hit pause now. All right, so the ball is moving horizontally at a constant velocity. There's no unbalanced force acting on the ball. So they're in the horizontal direction. So therefore the ball has to be moving at a constant velocity from side to side. However, in the vertical direction, it is accelerating down at the acceleration of gravity. So what we get here is we get two different types of motion for the same object. In the horizontal, it's moving at constant motion, and in the vertical direction, it is accelerating down at 9.8 meters per second per second. So think about this for a second and what that means for objects that have been launched with an initial velocity. So instead of just dropping a ball or tossing a ball straight up, now it's given some sort of horizontal velocity. What is the acceleration of that ball in the y direction or the vertical direction and the x direction or the horizontal direction? So what you should have come up with is in the horizontal direction, objects move at a constant velocity because there's no forces acting on them. But in the vertical direction, it is accelerating. So that brings us to our next little thing here, and I'm going to pause the video and get stuff set up for us. So imagine we have this scenario here, okay? You've got ball A and ball B, and you're going to have to forgive me because I'm having to draw this by hand, but ball A and ball B are supposed to be the same size, okay? So A and B are the same size, okay? The other thing is that A and B are the same height off the ground, okay? I know it doesn't look like it, the way I drew it, they're probably not. But here's what's different, okay, is that A and B do not have the same velocity, all right? So A is on a table and it's rolling horizontally. So it has an initial velocity in the x direction. It's going to go flying off that table perfectly horizontally. B is being dropped from rest straight down. The question is this: if A rolls off the table the exact moment that B falls, so basically A rolls off the table, B falls at simultaneously, which ball will hit the ground first? The answer here is, if you've been thinking about this, both objects will have the same acceleration because they'll have the same net force acting on them. They have the same distance to go, and so they will hit the ground simultaneously. Another way to do this would be to illustrate this by a dot diagram. All right. Object B's dot diagram would look like this. So there'd be a dot, followed by another dot, another dot, another dot, and let's say that's the ground, okay? Now, this is what object B's dot motion diagram would look like. Now, object A's motion diagram would look something like this. So if this was ball A would look like this. Excuse me, I drew that a little too far. Try that again. And let me see if I can clear this. There we go. Try it right there. Okay, so this is what object A would look like right here. So object B would look like this, and object A's would look like this. Now, you notice two things happening here. One is that as they fall, and I'm going to change colors here so that we can see this. Let's go blue. They fall at the same rate. So every second, they fall the same amount. Now, change it again to red. For object A, every second, you notice they go the same distance. That's supposed to be the same distance, all right, between each one. So object A has horizontal motion and vertical motion, where B just has vertical motion. What ends up happening is they both have the same vertical motion. Why? Because they both have the same net force acting on them. However, A has some horizontal motion at the same time. Its horizontal motion is constant, and it does not depend on the fact that its vertical motion is happening. Therefore, what we say is that the horizontal motion and the vertical motion occur simultaneously, so at the same time, but independently of each other, meaning they do not affect the other. The vertical motion behaves